Hi there, my name is Sasha Federova. I'm a professor at the University of British Columbia and a consultant at MongoDB. And today I'll tell you about my work entitled "We Replaced SSD with Storage Class Memory, and here is what we learned." So details of this work are published as a blog at this location, so you're welcome to refer to it if you need any more information. So this was part of the broader mission that I currently have at MongoDB, which is how to make use of persistent memory in MongoDB's storage engine WiredTiger. And today, of course, I'll talk about Intel Optane Persistent Memory, also known as 3D Crosspoint. As you probably know, persistent memory can be exposed to the operating system and applications as a regular block device. So you can write a file system onto it and pretend it's a regular disk and just mount it and use it. So I wanted to ask a very simple question. So if I use a persistent memory as a block device instead of an SSD, will WiredTiger run faster? So I wanted to have an apples-to-apples comparison. And so I compared SSD that used the same technology as persistent memory. So in one case, I compare persistent memory that is packaged as a memory DIMM and the same Optane memory packaged as an SSD. So in the first case, we have Optane technology sitting on a memory bus close to the CPU, and in the second case, it is sitting on a PCI bus, just like a normal SSD. And in this talk, whenever I say storage class memory, I refer to persistent memory packaged as a memory DIMM. So like in one of those movies where they first tell you what happened and then they untangle the story, I'm going to tell you that running our performance suite on storage class memory did not result in better performance. So now let's look at the experiments to understand why. We'll start by looking at raw device performance. Then we'll look at the effects of file systems and access methods. Then we'll look at the effects of the buffer cache. And then we'll look at the end-to-end experiments. So here's the raw performance with Optane SSD. There's no file system in use here. There's no kernel buffer cache. We're just opening the raw device as a file and reading and writing to it. So the y-axis shows the throughput in gigabytes per second, and x-axis shows the threads. The blue and green curve show the read performance, and yellow and orange show the write performance. We're using both system calls and mmap here, hence the two curves for each access pattern. But because we're bounded by the device bandwidth, there is no difference here between system calls or mmap. So according to the spec, Optane SSD should give us up to 2.5 gigabytes per second of read bandwidth and up to 2.2 gigabytes per second of write bandwidth. So we see that in case of reads, we do achieve the bandwidth according to spec. When we do writes, we go slightly above that. So there's probably some buffering going on here. By comparison, if you use a typical NAND SSD, the spec tells us that the read bandwidth would be up to 1.8 gigabytes per second, sequential bandwidth, and up to 0.6 gigabytes per second of sequential write bandwidth. So throughout this talk, when I show micro benchmarks, I will show you exclusively sequential access pattern. My overall conclusions about the random access pattern are not that different, so I do not include the charts here. But if you're interested, you can look at the blog post that I referred to earlier to look at the random performance results. Before we jump into the storage class memory experiments, I'll talk about my configuration. So a single CPU supports up to 6 memory modules, persistent memory modules. My machine, yes, and I/O scales linearly with each additional module, but my machine only had 2 of those. So that means that the upper bound throughput that I was able to achieve is limited by the limitations of my configuration. So let's look at sequential read throughput on storage class memory using only a single module. So again, the y-axis shows the throughput in gigabytes per second, and x-axis shows how many threads we used. So there are a couple of access methods here. DevDex is when persistent memory is exposed as a character device. And FSDex is when it is exposed as a block device, and in this case, we're using an ext4 file system on top of it, and we're accessing it in a direct access mode, meaning that there is no kernel buffer cache sitting on top. So the key takeaway here is that we reach just over 6 gigabytes per second of read throughput, as long as we use enough threads. And for comparison, the SSD with equivalent memory technology gave us about 2.5 gigabytes per second. And so interestingly, having a file system on top does not introduce performance overhead as long as we use enough threads. So now let's look at sequential write throughput, again with a single module. Now, the key takeaway here is that the throughput reaches only about 0.6 gigabytes per second, and there is no scaling with additional threads. Now, to remind you, read throughput gave us about 6 gigabytes per second. So write throughput is the Achilles heel of this technology. If I use 2 modules instead of 1 and compare the performance of the ext4 DAX access method using 1 versus 2 memory modules, we see that the maximum throughput that we're able to achieve is about twice as higher with 2 modules than with 1, both for reads and writes, although because the write throughput is so much lower, it is difficult to see on this chart. So what we learned so far is that Optane packaged as an SSD gives us up to 2.5 gigabytes per second read throughput and roughly the same write throughput. Now, Optane packaged as storage class memory gives us about 6 gigabytes per second of read throughput with a single module and roughly 12 with 2 modules, and only 0.6 gigabytes per second of write throughput if we use a single module. Let's now look at the effects of the buffer cache. So now we're going to use storage class memory as a block device, but we're going to turn the buffer cache on. So there are 2 sets of curves here. The top ones are storage class memory and the bottom ones are SSD. Now, even though we are using the buffer cache here, we're not really taking advantage of it because in this experiment, the buffer cache is cold. So we're reading through our data only once, but because the buffer cache is cold, there is no data in it. So we have to go directly to the device to access the data. So for each device here, there are 2 curves, and one One is using system calls and the other one is using mmap, but it makes no difference here which method you use because we're bound by the device throughput. So SSD achieves its maximum bandwidth here, 2.5 gigabytes per second. But storage class memory achieves slightly less than the maximum bandwidth that it can. So the peak device bandwidth was roughly 6.6. Here we're under 6 gigabytes per second, and it takes more threads to get to that peak bandwidth. So the reason is that when we use the buffer cache, so on the I/O path, on the read path, we read the data from the device, but also we need to place a copy of the data in the kernel buffer cache. So that's why this extra overhead prevents us from achieving the maximum throughput. But you can see we're not too far from the peak device bandwidth of 6.5 gigabytes per second. So what if the buffer cache is warm? So if the buffer cache is warm, we are essentially just copying memory. So it doesn't really matter what device sits underneath, because if all of our data is in the buffer cache and we have enough RAM to store all of our data, we're not going to device at all. So the reason why I'm showing you this slide is to highlight the difference between using mmap versus system calls. So using mmap is important here because we're reading the data so much faster that using a more efficient access method becomes sequential. So the main reason why mmap is faster is because it uses a more efficient memory copy that I use inside the benchmark. So when we use mmap, we're using a user level memory copy that's implemented in libc, and it is super efficient. It is relying on CMD instructions. When we use system calls, we can't use CMD registers inside the kernel, so we're using a less efficient memory copy to copy the data out to the user space. So this is an extreme case with a warm buffer cache and all the data staged there because we're not accessing the devices at all, but it highlights to us that if our caching is effective, then as expected, the difference between devices will be eliminated. So we just learned that introducing a buffer cache produces some overhead, but not dramatic, and effective caching will attenuate the differences between devices. All right, so now let's look at end-to-end experiments with WiredTiger. So this is a crazy big chart, and it shows basically all of the experiments from the WT-Perf suite that I was able to run. Now the y-axis shows you the WiredTiger benchmark names, and the x-axis shows the throughput in operations per second. We use mmap, and the OS buffer cache is on. So the yellow bars show the storage class memory with 2 modules. The red bars show the storage class memory with 1 module, and the blue bars show the SSD. And as you can see, there is no statistically significant difference for all benchmarks among these 3 access methods. There is actually one write-intensive benchmark where using the SSD is faster, and that is because, as we saw, storage class memory gives us a much lower write throughput than the equivalent SSD. So why did we see no performance difference from no performance improvements from using storage class memory? So in this particular case, caching plays a huge role. So we turned on the OS buffer cache, and in addition to that, WiredTiger also has its own internal cache. So we have not one but two caches here. And so if we run and WiredTiger makes a very good use of those caches. So if we ran without the buffer cache, so if we use the ext4 with the DAX option, so direct access, the throughput reduces by up to 30 times. So there are many factors in play here. We're using a complex software system with lots of threads. We're doing lots of things in addition to just accessing storage, but caching plays a crucial role here. The second factor is that we're running here throughput-oriented benchmarks. So each benchmark uses a bunch of threads, and they're all trying to get as many operations per second as possible. And so in terms of throughput, the difference between SSD and storage class memory in our configuration is just not large enough. It was less than 10x to really make a difference in the conditions when caching is rather effective. So what can we conclude? What's the insight? First, effective adoption of NVRAM will take some thought. So if you just take NVRAM and replace it as a storage, it will not necessarily make a difference. Not for all workloads, anyway. So do our results imply that NVRAM is just not a good replacement for storage? No, because keep in mind that we compared with a fast SSD, not your conventional SSD. So our workloads working set was not huge. It was, up to hundreds of gigabytes, but, not terabytes, which is the case where, DRAM may become short and you can benefit of having several terabytes of non-volatile memory, which would be cheaper than the same terabytes of DRAM. And in these experiments, we did not try to artificially limit available DRAM. Storage class memory will probably shine in latency sensitive workloads, because when we measured the latency difference between accessing an SSD and storage class memory, it was 100 or 200 times lower. And we do have to be careful about writes, because poor write throughput is still an Achilles heel of this technology. And that concludes my talk. Thank you very much.